Log on, tune in, find out. Another good idea from Cambridge.
Not even quite the last seminar, there's still another one tomorrow. Announce today's seminar. Andre Pinho from the north of Brazil is going to talk about strategies to analyse unreplicated factorial split plot designs. Over to you.
Thank you, Rosemary. First of all, I would like to say a special thank you to Rosemary and the organizers of this event to spending so much time and effort so we could all be here and participate in it. The second note is about Soren Bisgaard. Last week was the 2-year anniversary of his death, and in my understanding it was a great loss to the industrial statistics community. The last position he had was at the Eisenberg School of Management at the University of UMass in Amherst in USA. And what I'm going to talk about today is a application and strategies on how to analyze specifically two-level unreplicated factorial designs. This is just a brief overview of my talk. I will start with a motivation, saying why I think it's important to study split plot designs, unreplicated split plot designs, followed by a real application that was conducted at the University of Wisconsin in Madison, and then the identification of the location effects, followed by the residual estimation. I'm going to use the non-significant effects at the previous stage to estimate the residuals, and then with those residuals I can then perform a dispersion effect analysis. And I will finish my presentation showing an alternative approach to identify active factors. And when I say an alternative approach, it's an alternative to the one that I previously have shown during the presentation. Well, split plot designs are more common in practice than they appear. And the reason for that is they represent a natural way of running experiments in practice, especially when we have some set of factors that have some sort of restriction by changing the levels of those factors. I will show you in my example what kind of restriction that could represent. And since some practitioners, or I might say even many practitioners are not aware of the special feature that comes in when we have a multi-stratum design, and they end up not taking that into account. So they end up analyzing the experiment as a completely randomized design. And by doing that, they will most probably have a problem what we call misspecification of the location effects. When we consider the multi-stratum feature of a design, we may end up using less resources during the experimentation, and that can lead to some savings during the experimentation of a design. The data set that I'm going to show you was borrowed from Bisgaard, Fuller, and Barrios. They had teamed up with a group of engineers at the Engineer Research Center for the Plasma-Aided Manufacturing at the University of Wisconsin in Madison. And the group of engineers over there were having some trouble adjusting the process so they could produce a paper with a better quality. They were interested in using a plasma treatment on a paper. More specifically, they want to improve the susceptibility of the paper to ink. So they had several meetings, and after several meetings they were able to identify 5 factors to be used in the experiment. All those factors were used at 2 levels, all the factors. And Bisgaard, Fuller, and Barrios started to ask questions about the factors. and they were able to identify that 4 of those 5 factors were related to a reactor chamber that was not that easy to change. So by discovering this, they proposed a 2-level unreplicated split plot designs. And the whole plot factors that were not so easy to change in the levels were pressure, power, gas flow, and the type of paper. And the subplot factor was very easy to change, representing the type of material that would be put into the reactor chamber. In this case, is the type of paper. The response variable they called wettability, which consists of putting or placing a droplet of a specific liquid on a paper surface, and somehow with a microscope they were able to measure the contact angle between the droplet and the paper surface. And with that, they observed the 32 responses. We can see here that we have 32 treatments, but since they have chosen to run on a split plot designs, they only had to change the configuration of the reactor chamber 16 times. So that represents a big savings during the execution of the experiment. I'm presenting here the data in a standard order. However, they executed the experiment involving two independent randomization processes, one at this level and another one at this level. So, for example, they first selected randomly one of the 16 treatments. So when they select that particular treatment, another randomization would take place to specify which type of paper would be put in a certain position within the reactor chamber. And they repeated this procedure 16 times. Here I'm presenting a split plot model. In this case, in this particular case, we don't have this component here that represents replicates. This is an unreplicated design. And one of the features that cause misunderstanding in practitioners is the fact that now we have two sources of error. And we must take that into account while we are analyzing the design. This is the ANOVA table. And again, all the degrees of freedom related to replicates in this situation is going to be 0. So we do not have a formal statistical test to judge the significance of defects in this situation, the situation of the application. However, if we look at the effects of a particular stratum, we see that if those effects are not significant, what we are really estimating with that line is the variance of that particular stratum. The same applies if we go to the bottom part of this table. And that's going to give us some insight on how we can estimate residuals even though we are in an unreplicated situation. I find it useful to see the data displayed in such a fashion. We can understand better why we have two sources of error when we are in a split plot situation. I didn't put here all the 32 treatments, just the first 6, so we can have an idea on how we can use this in our advantage. For example, going back, the first path here represents the first line. So I apply one treatment to a whole plot unit. Since the whole plot units involved here, they are not identical, I ought to have an error source to explain this variation among the whole plot units. So once I apply the treatment, I'm going to split this particular whole plot unit in another 2 units, what I'm calling here subplots. And again, although they are coming from the same whole plot unit, they are not identical. So I ought to have another error source to explain the variation between the subplot units. And by adding those components, I can then observe my response. And the same applies throughout the other treatments. Here is the identification of the location effects. I have used the normal probability plot for each stratum, for each level. At the whole plot level, the effects that were judged to be significant were the main effects of A, D, and the two-factor interaction between A and D. Here we have the standard normal distribution quantities. So the scale here are in terms of standard deviation. So if I go up one standard deviation from the mean, I can have an eyeball estimation of the standard deviation in this dimension here, which is roughly 7. The same applies here at the subplot level. The effects that were judged to be significant were the main effects of E and the two-factor interaction between A and E. And a rough estimation of the standard deviation at this level here was 1. I can use now those non-significant contrasts or effects to estimate the residuals for each group. And I'm going to look again at the expected sum of squares to have a justification for doing that. But before I get into that, just a little bit of notation. In our case, we have k factors at the whole plot level, which is going to be, in our case, 4. We don't have a fraction, so p is 0. At the subplot level, we have just one factor, which is the type of paper, is 1. And r, again, is going to be 0 like p. So t represents the sum of the powers. In our case, it's going to be 5. I can express the sum of squares in terms of the estimated effect. And if I evaluate the expectation of the sum of squares, we can see that it depends on the effect. And if the effect is really 0, I'm estimating the variance of that particular stratum. Usually we are seeing the expectation of the mean square, but since we have a two-level design, the degree of freedom for each contrast or each effect is going to be 1. So it doesn't matter if I'm evaluating the sum of squares or the mean square, it's going to be the same in this situation. So after we have identified the potentially significant effects, I can have this table over here. And now I have 12 degrees of freedom at the whole plot level. And I can use those degrees of freedom to estimate the residuals for that particular level. And the same applies here at the subplot level. The residuals are going to be estimated by subtracting from the actual response everything but the non-significant effects at the subplot level. X as P stands for the matrix with all the effects that are significant. S here stands for significant. And likewise, when I'm going to estimate the residuals at the whole plot level, I'm going to subtract from the actual response everything but the non-significant effects at the whole plot level. So in each stratum, the only things that were left out were the non-significant effects that were judged to be in the location effect analysis. And with that, we can then move on and analyze the residuals in each group. At the subplot level, we didn't find anything that was, or it looked like suspicious to us. So we moved to the whole plot level. And there we found something that we did not expect. If we move from one level of C to the other level, we can see here that there is an indication of changing in the variation when we go from -1 to the +1 of C. But this is just a graphical portrait. I'm going to show also a quantitative analysis of this feature. So when we look at the literature, we found something that could explain that behavior, which is a dispersion effect. So changing the levels of a factor, the variation of the response variable seems to be changing as well. And there are several techniques that we can use to quantify the dispersion effect. The one I'm going to show you, it's a very simple one to use, which is the Box and Meyer. BM stands for Box and Meyer dispersion quantity. And since this measure has approximately a normal distribution, Montgomery suggests to use all the quantities in a normal probability plot. And here again we can see that the dispersion quantity related to C stands out from the remaining points, reinforcing the previous graphical analysis that at the contrast C, it appears to have a dispersion effect going on. The statistics of Box and Meyer is very simple. K here stands for a particular contrast. So once we have enough information to estimate the residuals for each contrast, we can then separate the residuals associated with plus signs for that particular contrast and the residuals with minus signs. And we can then calculate this expression. If D is close to 0, we won't have any indication of dispersion effect. However, if it's far away from 0, then we would have an indication of dispersion effect. So, but how can we judge if it's far away from 0 or not? That's where the normal distribution comes in. I can use that as a reference distribution to help me decide if the distance from 0 is large enough so I can judge it as significant. Conclusions so far. In the original technical report that I got the data from, they have identified the factors of pressure, type of gas, and type of paper as the active ones. We had originally 5 factors, but only 3 were judged to be significant. By studying the dispersion effect, we also find here that C appears to have an effect in the variation. And this was not present in the original analysis of this example. So this example shows us the importance of having a broader sense in the analysis by not just focusing on the dispersion, but also not only in the location, but also in the dispersion aspect of the factors. Because if we ignore this aspect, we may end up losing an opportunity to get a deeper understanding on the process we are studying. And if we lose this opportunity, we may not improve the process as much as we could if we have that broader sense of including also the dispersion effect analysis. In order to study the dispersion effect in an unreplicated design, I first have to identify the location effect. So I should use a technique that allows me to get the most information from the data set. And by looking at the literature, we found a Bayesian approach proposed by Box and Meyer, and we decided to use that in the same example. The scenario where this procedure would be most useful would be one where we have unreplicated designs, could be fractional or could not be fractional. The sparsity principle must underline the process. If we have many effects to estimate, starting with an unreplicated factorial design wouldn't be the best choice to start with. So the sparsity principle must underline the process. And I'm going to allow for no non-well-formed polynomials. Originally, they were considering just well-formed polynomials. What I mean by that is, if I have an interaction in a specific model, I don't have to have all the main effects of those interactions involved in that interaction in the model as well. So by allowing this flexibility, I will be able to capture more features of the design compared to other techniques.
Excuse me, I just want to make sure I've understood that.
Okay,
So you mean you're allowing an interaction without the main effect?
correct.
Okay.
And let's remember, we are at the screening phase of design. So what we are really interested in is separating what's really affecting not only the mean but also the variance. Once we know that, we can use more refined techniques to make prediction or estimation. Here is the posterior probability of the models after some calculations. Although it's somewhat big expression, all the components have a specific meaning. But I'm going to emphasize the last two. The last one represents a measure of fit. And the last but one, it's a penalty for increasing the number of parameters in that particular model. So the models with high posterior probability will be the ones with a good fit and few parameters in the model. And that's what we are looking for when we are adjusting models to a specific data set. Before I use this procedure in a split plot situation, this procedure was developed for completely randomized design. So there was just one stratum. So I need to have a response. But now I have two error sources, two stratum. So I'm going to two sources of residuals, split plot residuals, the whole plot residuals and subplot residuals. So I'm going to adjust the actual response in two groups, one representing the whole plot stratum and another one representing the subplot stratum. So I can then apply this technique here. And the adjustment is very simple. For example, at the whole plot level, I'm going to subtract from the actual response everything that belongs to the subplot level. Likewise, at the subplot level, I'm going to subtract from the actual response everything that belongs to the whole plot level. And again, I'm going to allow for the non-structured model or non-well-formed polynomial. So these are the posterior probabilities of each factor for the whole plot level and the subplot level. At first glance, the conclusion seems to concur with the ones we found at the normal probability plot. The effects of A, D, and E were the active ones. In factor C, we don't have any indication that this factor is affecting the mean of the response. But when we take a closer look, we see that B has some degree of activity. So I found it useful to share this remark that I extract from the paper. I'm going to highlight what I think is most important here. So when we are using the posterior probability, what we are really seeking is for patterns that may suggest new and interesting hypotheses not yet considered, such as B could be a factor that is not so evident as A, D, and E, but could present some changes in the response mean. Another feature, the absolute magnitude of the probability are less important than the probabilities and the relative magnitudes. And in practice, there is no harm done in interpreting these criteria probabilities liberally. If an effect or a factor is so evident, regardless of the technique we are choosing, they are all going to highlight that effect or factor as active. The problem is, what if it's not so evident, but it's also not zero? Can the technique also capture that behavior? So, the things that we are most interested in right now is simulating various scenarios, changing the degree that a particular effect or factor is active. And then we can be able to understand better and measure how good this technique is in identifying marginally significant effects and factors. We can also generalize to other multi-stratum designs because it was originally proposed for completely randomized design. We have shown you just an adaptation for split plot designs, but we can easily extend to other types of multi-stratum designs and implement those procedures in R. We had a setback recently. The hard drive of this computer was completely lost. I didn't have a backup of all files, so the files that had the program were lost, and I did all the computation in SAS. I used IML. The objective now is to not only to implement but also to make it easy to use in other multi-stratum designs. These are mostly the papers that I have used to prepare this presentation, and with that I thank you for spending part of your afternoon here with me. Thank you.
Thank you for that. So we now have plenty of time for questions. Anyone want to? Heiko.
One thing I did not fully follow is, you pointed out that your factor C had an effect on the dispersion.
Yes.
And I did not really see how in your Bayesian approach you tried to model that effect.
That's a good question. Here. The Bayesian approach is an alternative approach to the split plot, to the normal probability plot. And so I want here to identify the active important factors, not to study the dispersion effect at this point.
Okay.
Once I identify the location effects, then I will proceed to study the dispersion effects. Let's remember that if I misspecify the location effects, my dispersion analysis is going to be affected as well, because I do not have genuine replication to measure the dispersion effect. So if I misspecify the location effects, my dispersion effect analysis will be affected as well. So this here is just to applies just to the dispersion, the location effect analysis. I can iterate the method. Once I identify the dispersion effect, I can reweight the variance and see if those effects that were judged to be active are still going to be judged active. And then repeat the iteration until I don't see any changes.
But wouldn't it be perhaps desirable to do everything simultaneously?
I don't have replication. I don't know how to measure the dispersion without replication. I just have one observation per treatment. So I cannot evaluate if the dispersion is present or not without first identify the location effects and have a pseudo residual. So I don't know how to make a simultaneous analysis without having replication. For example, using mixed models.
I mean, you could, for instance, start with the assumption rather than, for instance, at the whole plot level, considering all interactions up to those involving all factors. Perhaps you say, okay, I may think that interactions involving 3 factors and 4 factors.
That's true. That's one approach, assuming that some interactions are not significant. But since they were doing that for the first time, we didn't have any prior knowledge. So I was not there. They prefer to see what the data would speak to itself instead of just assuming that some contrast wouldn't be significant. But yes, that's one approach, to assume that some of the interactions are not significant. And then we would be able to make a simultaneous analysis. Yes, that's one possibility.
I have a question, please.
Yes.
When you're answering Heiko and in your talk, you keep talking about an effect being significant. What do you mean by the word significant?
It's not a proper use of the word. I can go back here. It's a matter of judgment. Here, for example, I judge the effect to be significant, but it's not a finding based on a statistical test.
No, but you're still using the word, so what do you mean?
I have some evidence that this contrast differs from the magnitude of this contrast, of this effect, is different from noise.
Okay, so that's what you mean by significant.
Yes.
Thank you.
It's just an indication. But you are right, I should not use significant because I have not performed the proper statistical test.
Other questions? Hervé?
Yes, I was just having the same sort of questions on the ICO, and I wondered, because in the box on your approach, I wondered if you don't put a prior on the probability that the factorial term is active, and then
Yes.
As the probability of some terms being non-active is different from 0, then there is some place to estimate the residual variability in the Bayesian approach.
This part here comes from the prior probability of each model, and pi reflects the prior probability of a particular factor is active. Since I'm not indexing here, using any index, I'm using the same prior for all factors. And the suggestion I've got from the paper, it's pi around 0.25, 0.25 usually works very well when we are trying to come up with good identification of active factors. So in this particular situation, I have used the same pi for all factors, which is 0.25.
And when you say factors, do you mean main effects?
No, factors. Factors.
Well, I don't understand what you mean by factors. A, B, C, D, E?
No, the actual factors, gas flow, pressure, type of paper, and so on.
Yeah, those 5 factors.
Yes.
Yeah. So you really are only looking at main effects.
Not only main effects. As I said, the factor could be important in the model by the presence of an interaction. doesn't need to be important because of a main effect.
Okay, but then, so what do you mean then by the number? So are you thinking of AD as being a factor, for example?
No,
No.
that is an
So
effect.
this really is the number of factors.
Yes. Fi it represents the number of factors in the model.
First, your probability for the
The
interaction
T,
zero.
just a moment, please. Ti then represents the number of effects in the model. Could be an interaction, a main effect, but Fi is the number of factors in a particular model, which is different from Ti. Yes, please.
The prior probability for an interaction to be non-zero is then how big is that? So for the main effects, then prior probability is pi. What's the prior?
No, it's not main effect, it's factor. A factor will be active with prior probability pi. So I will have, and there is another assumption. A factor will be active independent of the other factors. So I will have a Bernoulli trial. I can think of
I
that.
think the reason we're getting confused is we don't understand the difference between a factor and a main effect. Is that part of, yeah. So when you say, what do you mean when you say a factor is active?
Let's see if I can explain myself better. Just a moment, please. Oops. For example, pressure. Oops. Yeah, could be here. Is the factor pressure important or active? If so, it's going to appear in the model through or a main effect or an interaction or both. Doesn't need to be the main effect. The main effect itself doesn't need to be significant or active.
I see.
When I say factor, it's more than just the main effect. The main effect is just one aspect of evaluating if a factor is active or not.
But then when you're choosing your pi, I mean, if you have a factor that is important in that sense and enters, say, pressure on its own, pressure with power, pressure and gas flow, and then you have another one which is type of gas which is not involved other than through its main effect, then pressure has a different weight in a sense.
Yes, that's why when I evaluate with the posterior probability of a factor, I'm going to sum up all the models that the factor appears. I didn't make this comment here. This normalized constant, C, here is the sum of all posterior probability where that particular factor appears in terms of main factor or interaction. That's how I can have or build this graphic here. I have summed up all the models where A appears, doesn't matter if it's in terms of main factor or interaction or both. And by doing that, I was able to evaluate the posterior probability that was close to 1. And C, again, is the sum of all posterior probabilities. Not just the ones that appears a specific factor, but all factors.
Can you just go forward to that diagram again, please?
Yes.
Yeah. So you said that you were allowing to fit the possibility of interactions without main effect.
Correct.
But here we've only got, I don't see any interactions in the chart.
Because I'm talking here about factors, posterior probability of a factor being active, not effects.
So it doesn't tell you anything about effects.
Yes, if I want to look at the effects, I have to unzip this graphic, if I say, and look at a posterior probability of a particular model. I will have so many models, several models. I decided to put them together just to identify the factors that were active, not the effects itself, but it can be done by just looking the posterior probability of a particular model. Here I have what I call it PJ, not PMI. PMI is the posterior probability of a model, a particular model. Here is the posterior probability of a factor being active.
Okay, so let me, is it okay? I want to follow up on this, and I'm afraid I need to write something. So supposing we have, say, a null model, a model involving A, a model involving B, a model that is just A and B, or there's a model that has both main effects in their interactions. So these are the models we could have if we just had two factors.
Correct.
So how would your, from the work you've done there, could we get out probabilities for each of those models?
Yes, we can.
And would the probabilities get bigger or smaller as we go up the diagram?
I don't know.
I don't have any feeling for
No,
that.
no, I don't have anything. Remember that the posterior expression for the posterior probability has two components: a penalty for increasing the number of parameters. So we just not should think in terms of increasing the number of parameters, I'm going to get a better fit. It depends on the penalty factor here, over here. So I don't have a feeling in advance which model is going to have a higher posterior probability.
So
Because of this penalty factor over there.
is that penalty something like you would get with, I can never pronounce it,
Active.
no, AIC, Akaike's information. How's it pronounced? Akaike?
Mhm. AIC.
Yes, yes. That has a penalty. Is that similar to this?
Yes, we can think of that. I never have thought about it, but it would be something similar, yes.
I think there is also, because you said pi is smaller than 0.5.
Yeah,
There is a
I have
penalty
used it 0.25 for all the factors. Pi is the
So there is
posterior prior probability for a factor.
There is a smaller probability when the number of factors increases in the model.
No, I can still. Yeah.
Yes,
Yeah,
pi
that's
plus
correct.
minus pi
Mhm.
is smaller than
Mhm.
1.
Yep.
So the probability should get smaller as it goes up.
For a factor to be active, pi represents the prior of a factor.
Yes, so now I'm asking about the probability for the models, which is what's there. And there they said that will get smaller when we put more factors in.
Yes.
Yeah.
Because it's going to be.
So as we go up the diagram, the probabilities should always get smaller.
Well,
Isn't that right?
originally I have 5 factors. So when I have chosen pi, I was thinking 5 factors, even though I'm just adjusting with 2 factors. Then I'm going to move to 3 factors, 4 factors, but my set of original factors are 5. I'm not going to change pi according to the number of factors that I'm actually adjusting at that moment.
Michael?
Can I just ask a practical question now? If you could again perhaps show this bar diagram with,
Okay.
I mean, if I understand correctly, so by using those probabilities, then you can just say in a very qualitative way, A is active, D is active,
Yes.
and so forth. Now, the underlying method is already quite elaborate. So I'm just wondering whether basically if the goal is only to find out in this qualitative way which of the factors are in a sense active, whether your initial normal probability plot or some other simple graphical method would not or give you the same information without having this additional Bayesian
Mhm.
work to be done.
Well, what we can gain by using a more elaborative technique is the fact that we can now be able to see things that we couldn't using normal probability plots. The examples that we have tried, we were not able to capture what I'm calling here marginally active factors by using normal probability plots. And with this, I could see some degree of activity. So I could be suspicious and give a further look at it. That I was not able to see with the normal probability plot, for example.
So where was the point B on that plot? Sorry. You got that?
No, I don't. You mean here?
Yeah.
Yeah. I don't know. I will have to. I don't know. Right now, I don't know. Which one represents B here?
But I mean, why can one be sure or hope that what one sees in the bar chart for B is not caused by random variation?
That's why we need to simulate to verify if we can really capture by changing the degree of activity of a particular factor. If we can evaluate that with simulation, we could infer, depending on the result of the simulation, that this here seems to be something that is really affecting the response mean, depending on the evaluation of the simulation. And let's remember, if this is really true, and we don't know at this point, we started with 5 factors, and only 3 or perhaps 4 are affecting the response mean. So the other one, which is represented by C here, in terms of mean, is not affecting. So I could use that to use your suggestion and have now information to have a simultaneous analysis in terms of mean. Because now I would have replication, because C is not changing the response at all. The response in terms of mean, location. Okay.
Carla?
You said that if you identify wrongly the location effect, it will affect the
Yes.
dispersion. So the idea here to try to get this marginal effect is to try to get a better
Yes.
estimation of
The
location
dispersion.
effect.
The dispersion. Because the dispersion, it's a conditional analysis. It's conditioning on the location analysis.
So, but here you're talking about the location.
Yes.
So if in the other using the normal plot, you couldn't see B.
Yes.
But if you don't see B, you may have a wrong location model.
I will have a
affect-
misspecification at the location model that will impact my dispersion analysis. So it's more elaborate, it's more difficult to make. But if this is really true that I can capture this behavior better, I will gain something by analyzing not only the location but also the dispersion parts of the design.
Is this helpful for the dispersion?
Yes.
But I mean, that argument can also be turned around, because if you include
Yes.
B based on that,
Mhm.
it should not be there.
Correct. That's why it's important in the simulation to verify out of a certain number of simulations how many errors I will make by identifying wrongly something that was not there, or the other way around.
That leads me to my other question. I think, unfortunately, you weren't here when Steve Gilmore gave his
No,
talk
I
at the Royal
wasn't.
Statistical Society. One of the main messages of that talk was that if you want to estimate dispersion, you must do it from pure error. And I was really worried by your suggestion that we first of all find out active factors and then say use the rest
Mhm.
to estimate dispersion, because surely that must be introducing biases.
We could. The point is, if I'm thinking practical terms, if people can find an excuse for not running an experiment, they will do it. So unreplicated design has its roles in practice. So if you want to study dispersion in unreplicated designs, I don't see any other way of doing besides estimating first the location and then the dispersion. It's not the ideal situation. Stephen Gilmore is right. We should use preferably by genuine replication. But what if we don't have it? We are not going to do it, or we can do something. The message is we can do something. And that can be useful in practical terms. It's not the ideal situation, I understand that. But by not doing it, we are not going to do anything in terms of dispersion effects.
Okay, well, there's a professional argument here
Okay.
as to how far we go along with people doing bad experiments and how far we say no, unless you take some more notice of me at the start, I'm just not going to help you analyze your data.
I'm not sure if unreplicated experiments are bad experiments. They not give me all the information at first glance that I needed, but I can do something with the data available, trying to get some useful information. I may not be able to, but I think we can still have some room to get some insights about what's really affecting the response, not only in terms of location, but also the dispersion. I think it's worth trying.
Okay.
I mean, in some places you said that for your approach it is important to consider those non-proper models.
Okay.
Why is that, or is it just...
If I do not consider non-well-formed polynomials, that's a good question. This posterior probability here, it's practically the same as C. I won't be able to see it. So by allowing non-well-formed polynomials, I can then start seeing things that I wasn't able to.
But when you've got quantitative factors, it doesn't make sense to put in an interaction without the main effect, because a change of units can change whether something goes into the interaction or the main effect.
Change the units?
Yes.
I didn't follow you, Rosemary.
Well, for example, if you change temperature units
Okay.
between Fahrenheit and Celsius, because the origin changes,
Okay.
what is A plus Bx, the A and the B change, and that has also an effect when you go into interactions. And so, gosh, I can't explain this well, but you should read John Nelder. He's written some very powerful things on why you can make a mistake over this if you've got quantitative factors. Could anyone else explain that any better? Or even know what I'm on about? I mean, if you have an equation, if you have an A plus Bx, and you replace that x, supposing we say x is equal to theta z plus psi, where we allow a change of origin, then what we get is a c psi plus b theta z. So you get this extra bit there, and when you start taking products, sorting out what is interaction changes, just depending on which units you are using. So I just wouldn't do that. Any further questions? Eve, are you about to?
No.
Okay, well, thank you very much
Thank
for
you.
giving us this talk.